Hello, so for my mobile robotics semester project, I have chosen to simulate the following paper, which is camera-based mapping in SAR via flying and ground robot teams. So let me just give an abstract of this paper. We have simulated three different stages that are defined in this paper. The paper is basically about obtaining different feeds via aerial and ground robots and then detecting victims in it, localizing them, and tracking their movements via Kalman filter. And that is what we will be focusing on for this project. Okay, so here's our project notebook, which goes through all the steps of the paper, most of them, and we will be looking at the results that I have simulated with real-time video. So let's first discuss the summary of our project. Once again, we have an aerial robot, an aerial drone, and a ground robot, but in places of robot, what we have done is just obtained an aerial feed and a ground feed, and then we have applied YOLO and KF on it to localize the victim. So once again, our project is divided into three different parts. The first is victim detection via YOLO, in which we'll get 17 landmarks. Then we have victim localization, which will convert our pixelated coordinates of the victim into real world coordinates. And then finally, we have victim tracking, which uses the Kalman filter to track where the person or the victim being tracked might go to. All right, so the first stage in the pipeline is victim detection, and how the paper does it is using YOLO, Ultralytics YOLO 8 nano model, which detects 17 different landmarks on a person, as this figure shows. And this is called pose detection. And here I am using YOLO 8N, and this requires some dependencies, so you'll have to install Ultralytics along with its dependencies. And so I'm running my model on my aerial and my ground video, which are two different views of the same person that will be moving around in our frames on which we'll be applying this algorithm. So we'll be working with one view for now. We'll be working with the aerial view, and the aerial view video has 494 frames in which poses have been detected. So some features that YOLO gives us includes drawing bounding boxes around the person, number of persons, and their landmarks, as well as the confidence level. So we've set a confidence of 0.2, shows that even if there's a 20% chance that the pose being detected as actually a person, then it will be annotated. So the next up will be visualizing what we obtained. All right, so here I have a video of a person that is being detected. She goes around in a circle, and the 17 landmarks are shown in the green dots. So you can see that her left leg is not being detected properly, and it just detects the green landmark. It puts it in place where her leg was supposed to be. So because of these reasons, we cannot pass these 17 landmarks all through the our filter and localize it. So instead of using these 17 landmarks, we'll just be using one coordinate to identify where the person actually is. And for that, we've used victim localization. So the way in which the paper goes is it uses symmetry and iterative methods to kind of assume where the landmarks would be if a person is actually being occluded via different obstacles. So you can imagine in a search and rescue scenario, a person would definitely be under rubble or be under trees, and all the landmarks may not be detected properly. So for that, the paper uses different methods to estimate the missing key points. However, the approach that I will be taking is based off centroid calculation. Over here, I have my get victim XY function. It gives me my XY coordinates for the person based off confidence weighted centroids. So for the paper, the centroid was the landmark, which was between uh, the right and left hip. But for us, the landmark or the victim coordinate would be kind of upward near the torso. So we can also visualize it. Let's first, the algo that we developed over here, my get victim XY, let's first run it on our XY coordinates that we had, the landmarks. And you can see we get a data structure, a list, which actually shows us our XY. So there's a tuple, which is saving our victim XY. So let's move on to the victim localization parts. Fine, we have detected and obtained our victim's actual coordinates in pixels, but what about in the real world? For that, we will be using something known as homography estimation. And what we will be doing in this case is converting our pixels into real world coordinates. So for this, what I have done is the area over which I was filming my aerial video, I actually measured the area. These 4 blue points will be my reference points in the real world that will show me the real world coordinates or distances between these blue dots. So for example, the top left blue dot over here is my reference point, which is at 0, 0. And then the rightmost blue dot over here uh, is my x. So for example, if I move in the x direction, then I have moved 11.5 meters here. In real world, this road is actually 11.5 in length from this blue dot to this blue dot. And then similarly, from this blue dot, my reference point, to this lower blue dot, the width of the road along with this entrance of the building is 5.5 meters. Then what I've done is I've also obtained the pixels of my image for these particular blue dots. And I have 2 arrays over here that actually showcase that. Then I'm simply using OpenCV's find homography function, which will give me my transformation matrix and help me convert from pixels into real world coordinates. So here's my function, which is actually doing that. And here I am calculating my victim's real world coordinates using my pixel to world function. So you can see for all the different frames, I have my victim's real world coordinates. And let me showcase this as well. Okay, so here I am actually running my random frame, so I can select the frame number. So let me say 200. And when I run it, it runs for 5 seconds. So over here, I've actually input this number in my wait key. Let me increase this number to better show the results. Okay, so my victim with reference to my world frame is at 5 meters and 1.2 meters. So you can imagine from this blue dot how far the person is. Okay, and then I also have an image over here which actually shows where my victim is with respect to this reference point of the world. Okay, so let's move on to our Kalman filter, which is the main essence of our project. So for the victim tracking part, we want to know where the person will be based off the measurements that we're getting from both our cameras in our paper. And in our case, we'll be focusing on just the aerial view. So our camera will be our measurement, and then we will be predicting based off our previous states where the person might be in the next coming frame. And that is where Kalman filter helps us. And in applications of SAR, we do want to know where a person might be going to, maybe to get rescue or shelter or running away from an emergency, from an accident. So let's discuss the different parts of a Kalman filter. So first off is the state definition and our motion model. the motion model we'll be employing is a 2D constant velocity motion model. And you might be wondering, where are we getting velocity from? Because we only have the coordinates x victim and y victim. Over here, if you check in your data, you can see that we had our victim world coordinates. And okay, so we actually have our victims x and y positions, which will be px and py for our state k. And then the velocity we'll be finding out based off the previous position and the current position, and then our change in time, which will be our frame step. So the paper uses our standard state transition model. So for my future state x, it is based off my state transition matrix A, which is F in our paper, times our current state, and then there is an additive noise as well, which is the process noise. And once again, this is normally distributed, and Q is something that we will be tuning later on. Moving on, I have my measurement model, which is the frames that I am getting from my aerial and ground views. So I have my observation matrix H over here, which is actually O in the paper. And what it tells me is that which sensor values are actually being used. So you can see there is kind of an identity in the first 2 by 2 elements over here, which shows that position of X and position of Y are being given, but the velocity is not being given by our sensors, which is our cameras. Then we also have R, which is our sensor noise, and we will also be tuning this and looking at the difference this parameter will have in our Kalman filter. One important thing to mention is that velocity is kind of a hidden state in our Kalman filter because you cannot track your victim based off just the positions. You need to know what direction they're moving on based off your previous state. So let's discuss the Kalman filter equations that are given in our paper. So first off, we have our prediction steps, in which we are predicting based off our previous states and our input matrices. E is my covariance matrix over here, as given in the paper. And then we'll be finding out the innovation, which is just the difference in our actual measurement, Z, from the camera, and then our correction. So next up, we have our Kalman gain, which is once again calculated based off our innovation, our sensor model noise. And finally, we have our update step, which will update our current belief based off the previous state and then our corrected measurement over here. And so is the covariance over here. Once again, as I mentioned, our noise, which is our process covariance Q, and our measurement noise covariance R, we will also be tuning these accordingly. Let's move on to our setup. Up here, I'm setting up all my matrices, my state transition matrix A, which is my sensor model measurement matrix, and then I have my tuning parameters Q and R. So I started by putting Q as small as possible and R as large as possible. Then I tuned it until I had a value that was the most suitable. Then I'm performing my prediction step, my update. This is again all the steps that we discussed above: the innovation, the Kalman gain, then our covariance update. Okay, so next up I have my filtering code snippet, which will actually be running my Kalman filter. Something different that I have done over here is use the frame stride, which will actually be using the modulus over here to use every 20th frame instead of all the 400 plus frames given. This actually replicates how a real world scenario would work because your Kalman filter cannot be filtering through every single frame due to bandwidth loss and frames that are not just reached in time. So instead of using every frame, you can skip off frames, and then we'll be looking at how our Kalman filter would be working. So first off, let me set this to 5, which will give us a much finer visualization. So I've also used CV2 to kind of visualize the path as well, which will show me different features that I want to see. So for example, prediction, update, and measurement. Let me run this to explain it better. Okay, so here I have my victim that is being tracked. You can see in the beginning my measurement, as soon as my measurement is detected, my prediction and update align accordingly. And you can see my victim is being tracked with the update and prediction lines. Oh, they deviate. Deviate over here where my YOLO actually does not work and detect the person. So it just goes along. I've actually pasted it over here. So it actually just goes along in a straight line. So this deviation was actually pretty large when I had not tuned my Q and R parameters. Similarly, I've also run the same filter for every 20 frame, and this is how my filter worked. So it may have worked much better. You can see there are lines, but it works much better for my for every fifth frame. So it means that the more frames I give, the better it works. However, there's also jitter that you can observe in your measurements that it's actually being smoothed out thanks to your Kalman filter. Let me also try changing my Q and R. So here I have my Q and R. Let me try giving Q a very small value, and let me try giving R a very large value, maybe 40. Let me run my function again for Kalman filter and run my filtering again. So it works pretty slowly for, and there you go, it deviates again. So you can see it's way far behind, which just shows that we gave it a way bigger noise covariance. So let me maybe reduce that to 20 and look at the results then. Okay, they get aligned, and then your measurement is being followed much closely now as it was before. And there you go, it deviates again. So you can realize how I reached these parameters after testing and everything. So the best parameters are once again 3 and 20. So this was all for the project. Another aspect that the paper actually covers is a Z frame as well, which will tell you how far away a person is from the aerial camera. For that, I have actually also obtained different specifications. So for example, the length of the victim in inches, and then the actual length, as well as the camera specs that I used. So field of view, horizontal and vertical for both the cameras, and then their distances from various reference points that can be used for future work. So this was all about the project. Thank you.